Okay, well, I hate this resolution up there. Digital class. And I'm not going to spend a lot of time on these slides because my point here is jump here. I want to kind of jump ahead here a little bit in these slides. We'll come back to here later, but okay. All right, where I want to talk about is there's a whole family of devices. We're not going to spend a lot of time talking about them. They're not necessarily part of this class per se, although they are a very important part of the industry. Matter of fact, they've actually taken over in the industry when we start looking at programmable logic, or PLDs. These are devices that are programmable in the sense that when I plug this thing in, it's going to have a default configuration in it. And in the case of this one here, it does all kinds of funky things right here. It's just we're testing that there. So when I want to do something with this, I have to download a configuration into the board. So the device is what we call programmable right there. And there are multiple types of programmable devices. There are those that you can program and take the power off and the program will stay in there. Now when we say program, we're really talking a hardware configuration. We're not talking a program as in a computer system. We're talking about, we're telling the device how we're going to set the hardware up, And so these PLDs are very commonly used, and for the most part, they have really replaced TTL parts in 90% of all electronics out today. So the labs that are talked about in the books and the chips we're talking about in the books, you can't even find them anymore. But we use the same technology, design techniques, but we use this type of hardware. So I want to kind of go into the hardware. They use a type of switch matrix right here, and this is for a combination logic. So we have A coming in, and then we have an inverter. So an A naught comes down here. We have B coming in, B naught coming down here, and we go all the way down through to however many inputs we have, and we can have 100 inputs if we wanted to. So we have 200 lines there, and then we have all of our product terms here. And we either put a short or don't put a short there if we want to connect that there, right there. So if we want to connect that there. And these only show 2 input AND gates, but they can be more than 2 input AND gates. And then, of course, these would then all feed into an OR gate for the output. So what we configure, and I thought I grabbed my pen, but maybe I didn't grab it. Yeah, there's my pen. So the whole idea is that we have, here's our inputs here coming in, and then here's our inverters right here. And we have, these are all brought down, however many there are, blah, 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 a bunch of these. We have a bunch of AND gates here, however many we have, and then they feed into one OR gate right there. And that allows us to do a sum of products term from any truth table right there. And we don't have to have individual chips. All we have to have is the truth table. And the software will then take the truth table and develop the circuit, set the configuration for us for that right there. And that's the simplest form of PLD right there. And up right there. So as we look at this right here, this is a basic PLD right there, and it has nothing but AND gates and OR gates in it, along with a couple inverters right here, So by deciding which intersections are connected, we can, quote, program this to have any type of output we want. So this is a PLD. Now, this is a relatively simple one. This actually, as if you look at it, is this particular one right here, right there. If you look at the picture right there, and it connects this to the PC for programming. And then there's also out-of-the-system programmers that you can put the chips in and program them and then drop them into your circuits right there. So these are this is the type of technology that's actually being implemented today. And I kind of wanted to step away since I've got a migraine coming on, and if I start doing ones and zeros, I'm probably going to just mess them up anyway. So I figured I'd talk about a topic that I could probably not screw up right there. So that's it. So we basically connecting to the 4 pins, the IC remains in the system, interface cable loads in, we can program this directly into the system. Now this is into a development board. I should point out that when we design a PLD type system, we can design it with the programmer on the final system board, so where it can be reprogrammed in the system out in the field. We can change the design out in the field, or we can leave those pins off. It's only 3 or 4 pins that's involved. It's plugged, this is plugged into a USB serial port, and there's a little chip in here that interfaces that there. So this has got the program built into it. There are also ones that don't use the USB that will talk directly to the chip and don't need any configuration cable on the board. So we can actually configure these things multiple ways depending on how often we want to reprogram this. I've used these in multiple systems in the past. I've used them in one system we worked at. We left the programming heads on the final design. We shipped the units out to the customer. We made design modifications. We showed up with a laptop computer and changed the design out in the field. That there. So it's very, very flexible in that way. The Altera Max++2 is a development software package. We're using a software package called Quartus. Quartus is the successor to the Max++2. Max++2 has been around since the 1980s, late 1980s, early 1990s. It was replaced with Quartus somewhere right around the year 2000, 2001. That's there, and it's the same software basically that they're talking about here. So I'm going to be showing you the Quartus software. I probably have used it in the past. We're doing the simulations right there. So we can do hierarchical design with the software. Hierarchical design means that we can design a schematic right here. That's what we've been doing thus far, is we've been drawing schematics. We could use something called VHDL, which I'll talk about later in the semester. That's the basic hardware design language right there. We used to be able to use a timing block. That was a feature of Max++2. They took that out when they came to Quartus. Nobody used it anyway. It was pretty much worthless. It was useless. And then there was a language called AHDL, which is the Altera hardware design language, and that's more or less disappeared there. Now that's been replaced with something called Verilog right there. So we can also, we basically have multiple ways. Typically we use VHDL or schematic block are the two that we use with Quartus. Except for we're in Malaysia, and Malaysia doesn't use VHDL so much, so they tend to use Verilog more. When I talk about those are two hardware design languages, and they're a little bit different from each other. VHDL, is the one I'm going to talk about simply because I know it better than anybody else. Than Verilog, since I know it, that's the one I'm going to teach. Unfortunately, it's not the one that's going to be used here. I probably should learn Verilog, but it's also the one that's used in all the textbooks that we have. Most of the textbooks do not talk about Verilog because almost all the textbooks come out of the U.S., and the U.S. uses Verilog very seldom. They use pretty much nothing but VHDL. Asia tends to use Verilog more than VHDL. And there's a reason for it, and it's very simple. The U.S. Department of Defense paid for VHDL to be developed, and they say if you do any work for the U.S. Department of Defense, you have to use VHDL. So as a result, almost all American companies use VHDL. Therefore, since all the textbooks are coming out of the U.S., they all cover VHDL. Verilog's a little bit easier to use, a little bit less cumbersome. Anything designed by the U.S. government has got a lot of garbage in it that doesn't need to be in there. Just like anything that comes out of pretty much any government entity. So I shouldn't pick on the Malaysian government entity, but they're just like any other. You know, it only took me a month to get a driver's license translated. That's there. So I mean, so anytime you're dealing with any kind of government entity or military entity, it tends to be more cumbersome. So if you're designing, say, chips for television sets, you know, if you can save 2 or 3% by going with Verilog instead of VHDL as far as time goes, they'll use Verilog. So companies like Toshiba, Hitachi, Samsung, they're going to use Verilog. Companies that deal with any kind of military aspects are going to be using VHDL. Since my background in the real world has been more toward the military side, I'm more of a VHDL person. That's there. You know, I've done more military work in the early part of my career than I did commercial work. Toward the latter part, I did a lot more commercial work, but even then, it was in the U.S., so pretty much everybody was still using VHDL. That's there. So we can design hierarchical and put different blocks within. That makes our designs much more efficient, much easier to manage when we get into larger designs. And we'll talk about that later on. I have a lab that you'll do, say, with an adder, where we design a simple adder and we have combined them up to make a 4-bit or an 8-bit adder by just simply adding the blocks up there. Top down means that we can design each section separately and tie it into the single chip right there. So top down design means that we're designing a DVD player in this particular case. Up there, the DVD player has the audio and video section there. That's the analog part of it. We have some D to A there. We have some digital processing. We have filters and amps, memory. We have our laser that has to control the motor, skip, the pulse train, position control. We have to move the spindle. So we got various parts of our system that we design, and each part of the design can be assigned to a different team, tested separately, and then put into a final IC. Now remember, this particular one here, these are all subsystems. But has anybody looked inside of a DVD player lately? You don't see a lot of electronics, do you? You see one large chip, right? That's one large ASIC. So all these used to be individual boards or subcircuits. Now they're all part of one chip right there. So, and tools such as Quartus and the Xilinx equivalent and those cadence, those tools have allowed us to design these very complex chips by breaking it into subsystems. Otherwise, this is too much. If one engineer had to sit down and design the entire operating system for a DVD player, you're talking a lot of work out there. And keep in mind that not everybody's specialty is, for example, the audio visual. You're going to want somebody with some digital signal processing capabilities that understands things such as video encoding, decoding, audio decoding, you know, because you're taking an MP4 file or you're taking a bit stream and you got to convert that to video. That takes a set of mathematical skills that not everybody has and not everybody needs. Same thing if you're talking about controlling the laser, you know, the tracking system on the laser. That requires somebody who's very competent with servo motors or very competent with stepper motors, positioning that there, you know, that there. So there's there's different skills involved in different subsystems. Not every engineer is going to have every skill set there is for designing every system. You're going to, you know, I've worked with engineers that did nothing but design power supplies. That's all they did in their career. 35, 40 years, they designed switching power supplies, linear power supplies, DC to DC power supplies, AC to DC power supplies. They knew power supplies inside and out. That there. That's what they did for a living. That there. So they designed power supplies for aircraft, power supplies for submarines. They designed power supplies for refrigerators, but they designed that there. This is the timing simulation. I'm not going to get into that in too much detail. That's there. This is kind of the way that we go through the process. I'm not going to go through that. I'm going to go through an example here, right there. So, that there, we typically are going to be working in hexadecimal numbers when we're working with these right here. So we will be working with hex. That here they're talking HDL and VHDL, that they use a little slightly different. Note that there again, you know, HDL has disappeared for the most part, so I'm not going to talk about HDL. I used to teach this course, or the advanced version of this course, almost all in HDL. I loved HDL. It's a very simple, easy to understand language, but they took it away. Right there. So let me just jump out of this here. You know, these slides get into the syntax. I'm going to jump out of this right here and jump now into the software and talk about a relatively simple design right there. So let me just go through a simple design. And I thought I had the Quartus thing there. Nope, I don't. I know it's over here, so there it is. This is the Quartus software. I may or may not have had it up in this class. I can't remember. Since I'm teaching the same course 8 weeks ahead of this class, I can't remember what I've covered in this class, what I've covered in that class. Up there. So this is what the software looks like right here. It actually looks much better on your computers in the lab, and we will find a lab to do some of these with right there. And I think I mentioned Thursdays is probably the day that we'll be using the labs. I think it's booked at this time on Tuesdays. Okay, I'm going to just draw a simple circuit here and go through the process of how we go through that there. And I don't necessarily care that much about whether it's the simplest circuit or whatever. I just want to go through the process. That's all I'm going to go through right here. So I'm going to create a new file, and this is going to be a block schematic file. I'm going to draw a simple Boolean expression type circuit right there. Right there. So we're going to have 4 inputs. Input. And I'm going to say auto repeat because I'm going to put 4. Now, unfortunately, our screen resolution is horrible using the projector, so I'll have to move this around a lot. Up there. When you do this in the lab, you'll find that it actually looks a lot better. Right there. And I'm just going to put in a random function right here. I'm just going to call A naught times B plus CD, okay? So I'm going to put in a not gate there. So this is going to become A naught right there. Let's put in 2 and 2s. 1 here. And then another here. Let's put in an OR 2 right here. And let's put in the output right there. And you can bring this here and pull it back to connected. And this is a little bit like multi-sim, if you had multi-sim on how you would draw this right here. Right there. A, B, C, D, we named our pins, and we'll just call this X out. I don't like to use X because if you use HDL or VHDL, X means don't care. We really haven't talked about don't cares in our Karnoff maps, but you know there are you know, in our Karnoff maps we had things such as ones and zeros, there's also a third input we can have, and it's a don't care, because you don't care about that input for particular reasons right there. So X means don't care right there. So this is the circuit A naught B plus CD right there. So we're going to go ahead and I'm going to implement that on this board, and we're going to need to test to see how it works. Now, unfortunately, when I run this on the board, right there. So let's go ahead and save this, save as, and designs right there, and create a new directory for it. I want to put it in designs, and I like to create a new directory for this, and I'm going to call this digital September 29, right? Actually, I'm in Malaysia, it's supposed to be 29 September, right? In the West, we always do it the other way. 15. That there. And I'm going to call it the same name. Save. Okay. I want to create a new project for this. And when I come up with this, now I'm going to have to unplug the projector from time to time here, simply because I can't get down to the next button. That there. So the working directory I created, digital1-29September15, the name of the project is that there. I'm going to go ahead and unplug that and hit next right here. And I'm not going to add any additional files, so I'm going to hit next again right there. This is only going to have one file. Now I'm to the point I have to pick a part for this right here. And this is always the tricky part. Where is my projector? Okay, this is the tricky part, because here's where I rely on good eyes. There's a part number on this part. I can't see it, so hopefully I can see it on the data sheet. Right there. Right here. So, right here's the part number, and it's blurred on the data sheet. But, all right. Fortunately, they tell me the part number here. So this is a Cyclone 3 EP3C16F484. That's the part number on this particular part right there. So, and if you had good eyes, you could see it written right here, if that wasn't blurred. And I know I can't see it here because the lights are off, but let me see if I bring it here whether I can see it. Nope, I can't read that. Who's got good eyes? Can you read that number on that part to see whether it matches that there? EP3C 610? Okay, all right. Well, if there's no way, that picture's not sharp enough. Actually, the best way to do it is to take a picture with my phone out there and then look at the picture on my phone. But unfortunately, that's, you see, they tell us what the part number is. It's right there. They don't tell us the full part number. They tell us the general part number. All right, let's go back and see whether we get close enough here. So this is a Cyclone 3. It's a 3. It's Cyclone 2. Cyclone 3, 3C5 Let's go back to our data sheet here. It's a 16F44. F484. And you said it was a C6 is what you thought it said? Let's check back here. I think it's a C6. It could be a C7. Yeah, the last part of the part number is the part one that's tricky. C6N. I actually have better glasses for that. I don't have my actual reading glasses here. Can you? I think it's a C6N. C6N. I'm sorry. For those that are laughing at me, remember, you will turn 50-something one day, and you'll have the same issues. That's there. Some of your parents. So the N doesn't matter, but the C6 does matter. So next, and finished. Okay, so we've selected the part right there. Now we've got a couple other things we need to do. Our device we've selected right here. I also set our use input. Yeah, okay, that's set fine. Okay, everything's fine. Now, I'm going to go ahead and compile this right here. And what the compiler does is this fits it into the part, is what it's going to do. Now, it's going to give me some warnings. We'll talk about the warnings in a few minutes. I'm hoping that Thursday I can get the other room, and you can do this on Thursday. Not there. Okay, we got 9 warnings. No clocks defined in the design. All right, this is async. This is just a Boolean expression. There aren't any clocks, so we're not using any flip-flops here. No clocks defined. No clocks designed. There's no constraints file, which we're not going to. We don't get into that here. No clocks. We have not assigned our pins yet, so we will have to assign our pins. Right there, feature lock. Okay, so none of these warnings are anything we have to deal with. Right there, none of these warnings we have to worry about. So once we have this here, we can go through it and simulate and see what it does. Before we simulate it, we have to create a new file. This is called a vector waveform file. Let me close this here. We list all of our pins. We move them over. Right there. So there's our vector waveform file, A, B, C, D. I'm just going to group these together. And the reason I group them is just simply so I don't have to draw them individually. Right there. Now, before I do anything, I have to do a couple other things. I'm going to set our end time to say 20 microseconds. It doesn't really matter. That's probably more than I need. And then I set my grid time to say 100 nanoseconds. And I'll explain why I do that in a minute. That's there. So then we go through here and we're going to say bit order. Our most significant bit is on top. That's fine. Okay. And then we're going to set our value, and we're going to have a count value right there. And what we see here is that A is our most significant there, and we can see it counts from 0 to F and repeats, and 0 to F to repeats. So we can more or less see our truth table there, right? So now we're going to go through and we're going to save this and simulate, and we'll see what our truth table would look like up there. right there. So this is what our truth table basically looks like right here. Is that 0, 0, 0, 1, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1. So that's what our truth table should look like. And again, one of the assignments would be is to go through and verify that's what our truth table should look like right there. So now the next task we have is we have to look at our pins right there. So this is ready to put down into the chip. Unfortunately, we don't know our A, B, C, D, and X out are on the chip. This chip has 484 pins. So we probably should tell it where we want A, B, C, D, and X out to be. Now, if you look at this board, it's got across the bottom of it 10 switches right here, and it's got some LEDs. So that looks like a good place to put A, B, C, D on the switches, and to put the X out on one of the LEDs, right? Now, these numbers are going to be different than the ones on your boards. Your board's bigger than this one that's there. So, actually, in the U.S., when I taught this course, each student bought a board that there. They sell for $80 U.S., which at one time was about 250 ringgits. Now, $80 U.S. is about 500 ringgits, right? But we won't compare U.S. prices today with the current exchange rate. It's not good. That's it. So, but let's go ahead and we pull up our data sheet then again. Right here. And in this data sheet, we have buried way back here somewhere. Right here. We have our switches here. There's our 10 switches, and we're using A, B, C, D. A is our most significant switch, and I'm going to all right, switch 0 is there, so I'm going to use switch 3 through 0 right there for A, B, C, D. Okay? So, in doing that, and I didn't bring a pen, J6, H5, all right, someone write these four numbers down for me so I don't have to keep going back and forth. A goes to J6, B goes to H5, C goes to H6, and D goes to G4 right there. So we go back to our software, and we pick assignments, pins. A goes where? G6. A6. Juliet 6. B goes H5, Hotel 5. C goes H as in Hotel 6. Okay. Okay. And D goes ground floor. And now we go back to here. J6, H5, H6, G4. That looks right. Okay. And then we're going to just use J1 for LEGG0. J1. J1. So we've assigned our pins right there. So now we go through and we recompile. You always have to recompile after you make a change. Right there. This time we won't have that warning about unassigned pins. That warning will be gone. We'll have another warning say that we did not tell it the capacitance and the resistance of the pins, but we don't care about timings. So our warnings are down to 9. We look at no clocks, no clocks, no clocks. Our constraint files are not there. We don't have a constraint file for this here. No clocks. Constraint files missing. Have some complete up there. And when we look at that there, we'll see what that means up there. right there. So if we go here to the fitter, right here, right here, this shows us where all of our pins are, and you see there's lots of pins. As I said, as you look at this file, there's 484 pins, and right there, and they start with AA, and you can see X out is on J1. Remember we set it on J1, right there. The input pins right there, this is the easier one to see where it's at. So J6, H5, H6, G4, our output pin is on J1 right there. So those files are easier to find. You see, and this actually tells us coordinates on the pin for doing the PC board and all that there. So now we're ready to program the board. So we plug in our board, we turn it on, and trust me, it won't be this simple the first time you do this, because programmer, right there. And this sees the programmer right away. It sees that we got the right chip right there. And by the way, that C6 it doesn't care about anyway. We spent all that time worrying about the C6N, and it doesn't care about that anyway. So we start this. Now the board has now been programmed right there. So we can close this, open that back up. And what I'm going to do is go back to our simulation right here, right there. And I'm going to flip switches to see whether or not we get the right thing. Now, if you're watching this on video, you can't see the LED. But right now, all my switches are to the bottom, right there. And right here, let me go to right here. Here's my switches on the bottom, right here, and I'm using these three switches right here. A, B, C, D. Down is logic 0, up is logic 1, right there. So, using those three switches, Alt-Tab, right there, we go back to here, and we can see 0, 0, 0, my LED should be off. We don't have an LED on until we go to 3. So, 1, and, okay. Don't tell me I got a bad board here. You can see what happens when I get a valid input. The LED comes on right there. So, actually, I think I got these switches backwards because that is right there. Because as I'm looking at this here, that's 3. All right. Give me a second to look at the switches again. Make sure we got these things set right here. SW0, SW. And I don't want to unplug the board because let me go back to the run program. What I'm wanting to do is look at the board. Unfortunately, with the angle of the board, it doesn't necessarily show me whether this is 9 to 0 or 0 to 9. So I'm going to have to unplug the board and get under the light. I did this once right here. Okay, that's 9 to 0. This is 0 here, so 0 is on the right side. Unfortunately, I have to reprogram the board. Right there, that's not a problem. Okay. So A And we program these. Let's go back to my right there. Let's make sure input pins. A is a J6 right there. J6. J6 is A, so that's the one all the way to the right. Okay, I got them backwards that there. A is a J6 right there, so I've got them backwards that there. I meant to put A on G4. That's probably easier to fix the design, so I'm going to have you read those part numbers back to me the other way. A should be on G4, right? And this will probably give me that there. I'm going to, this one here, let me just delete these assignments and start over again, because I can't, well, it's going to yell at me if I. So this is G4. The next one was at H6. H6, is that right? And then the next one is H5. And then this one is J6, right? Okay. And if I had $1 for every time a student did that, I would have been able to retire 5 years ago. If I had $10 for every time I did this, I could have retired 2 years ago. That there. So it's okay. Hopefully we got it right this time. If not, all right. Now, yeah. Okay. Now I got it right. So 0, 0, 0, I got no output. 1, no output. 2, no output. 3, I have an output. 4, I have an output. 5, I have an output. 6, I have an output. 7, I have an output. 8, I have no output. 9, I have no output. 10, I have no output. 11, I have an output on B, right there. C, no output. D, no output. F, an output. So I get the truth table out that I expected to get out, that there. So that was the whole goal of this whole exercise, is to verify in hardware what we would expect to get, that there. So it's kind of a lot of steps to go through that. But trust me, this is easier than building a circuit and wiring and moving the wires from VCC and ground, or putting the switches. As our circuits get more complex, you'll be very happy to have these boards versus doing them by hand. That there. So, okay, well, as I said, it was going to be relatively short. It wasn't that short, but by the time we went through everything. But that's the whole process of implementing a design in Quartus and putting it onto the hardware and test, verify. We put it in the design. We just drew the schematic. We compiled it. We simulated it. Got there. We assigned our pins. We programmed the part, and then we tested the part on the board. And everything worked exactly as planned, except for I reversed the pins. And that will not be the last time I do that this semester. That's there. And it's by far not the first time I've done that. And the experience is, as soon as I started playing with the board, that wasn't the right thing. I knew where to look. That's where the experience is. You know where you make your mistakes. As engineers, you will make lots of mistakes as you go through this up there. You probably have made a number of mistakes in your labs already, right? Not every lab worked right the first time. Whenever I read a lab report and a student tells me that it worked exactly right the first time, I'm thinking either somebody else did his lab for him, or he just got awfully lucky, or she. I shouldn't pick on that there. So, with that said, that is probably my